we were talking about the temperature correction factor tables in National Electric Code, and we learned that one of the most important things is to read the actual heading, because in the heading there's a qualifier to this chart that's at a certain temperature range, and as we'll see in just a bit, this same chart will appear multiple times in code. And if you do all of your calculations based off the chart that's at 86 degrees Fahrenheit, whenever you go into other tables that have to do with other kinds of ampacity derating, you might get different temperature ratings. You need to make sure you look up in that title and make sure your temperature is matching. It's, to me, I think it's kind of confusing that they have these kinds of different charts, because you'll get to the same point whether or not you use all the 86 degree Fahrenheit temperature charts or you use all the 104 degree Fahrenheit temperature charts. The end result, the end sizing calculation will be exactly the same. Anyway, we'll get into that in a minute. How do you read this chart? We basically, the hotter in temperature you go, you need to start having higher temperature rated conductors, to the point where lower temperature rated conductors, when they begin to exceed their temperature rating, code is saying, that 60 degrees Celsius cable cannot go in a 80 degrees Celsius, environment. Otherwise it'll start burning up. Remember, those cables already generate their own heat from the electricity inside them. And so, by the time you get into extreme rooftop temperatures where your cables are 1 inch from the rooftop, you have to be using 90C rated cable just to have something that can be safe up on the rooftop. But actually, this isn't so bad, because it's not just ampacity sizing in cables. It's the friction of the electrons as they're flowing through on the cable jacket itself results in losses called voltage drop. So you often upsize solar cables anyways because of voltage drop. So you could easily be up on the roof using 30, 40 amp cable for an 8 amp circuit, and it'd be perfectly fine in terms of the conductor being able to withstand that extreme heat. Because only a third of the tube that's inside of it is full of electrons, and the other 2/3 are helping those electrons travel through and dissipate that temperature. And what we also see kind of on the other end of the spectrum is, if we're using high temperature rated cable in a cold environment, it's giving us a the original calculation, the 100%, is done at this like 86 degree Fahrenheit. And so if we're actually at a lower operating temperature than 86 degrees Fahrenheit, we get to add ampacity capacity into the cable rather than subtract it. So here we have a different table, and this is much further along in this same kind of section 310 of code. We see this ampacity table at 310.15, then a couple pages later you see at 310.60, the same ambient temperature correction factor chart, except it's done at 104 degrees rather than 86 degrees. Like, I have deja vu or something. I thought I just saw that. Well, it's the same chart. The only thing that's different is all of these fudge factors have been calculated based off, assuming that the starting point temperature is 104 instead of 86. And that's the only difference. So it's kind of weird. The most important thing is to be consistent and make sure your temperature title matches. So I just think it's most convenient to just start with the chart that's up first and use the lower temperatures and higher temperature derate factors. And so what we see here is, instead of calculating this table using 86 degrees as a reference point. We've calculated the same table using 104 degrees as a reference point. And since our starting reference point was higher, when we get into real ambient operating temperatures, we don't have to derate as much as if we're using the lower temperature. And so because these fudge factors were calculated based off a higher reference point, you don't have to discount as much because you've already built an additional 20 degrees of Fahrenheit into the fudge factors. So it can be kind of confusing if you're just looking at these charts and say, when do I use this or when do I use that? You just have to read the titles. Stuck in these title addendums are additional details. Like you'll get ampacity charts for conductors inside of conduit versus in free air. And that, because a conductor in free air has much better temperature dissipation than inside of conduit, will have a different ampacity rating than inside of conduit. So you have to read the title, the chart title headings, and make sure that the modifier in the title heading kind of makes sense for your case. So in addition to the difference between a conductor being inside of conduit versus in free air, that would be one difference in operating heat. Another would be if you have multiple cables carrying heat bundled together, whether they just be thrown in the ground or inside of a conduit, perhaps even outside of a conduit, depending their spacings. But this says, look, when you have more than 3 cables bundled together, you have to further derate its ampacity. Actually, not a huge deal. I don't, the reason why some of these tables are incomplete is I can't give you a complete copy of National Electric Code for you just to print out and have as a handout, unfortunately. So there's middle data, inside of here, but what we're trying to do is illustrate the point. The more conductors you have bundled together, the greater the derate. So we see starting at 4, you have to derate by 20%. And then once you get into a couple dozen conductors, you're derating by over 50%, 55 to 75%, or 65%. So actually, if you have a whole bunch of solar circuits that are oversized because of voltage drop, and you're not, and then you start bundling them together, that starts to get into, okay, well, am I bundling it to go across a walkway, or am I, is it going to be a short section? Is it a bundle that might be 1 or 2 feet, or is it a bundle that is 10 feet long or more? You have to start applying these derating considerations. Actually, 3 feet or so. So then we have so ambient temperature correction factors. I guess we've maybe this is a redundant slide. We've seen this already. Okay, so now we're getting into, so this is still like section 310. Remember, this is wiring, and so if you're flipping through codebook, if you don't need to memorize the actual individual numbers, but if you know that section 300 is the wiring cabling section, and this is pretty basic stuff, it's going to come towards the front of the section. Then you start thumbing through your charts and then reading these titles. So this one is based on 86 degrees, and then separately there's another chart that's based on 104 degrees, and then says the ampacities in this chart are for no more than 3 current carrying conductors, because otherwise you'd have to go and apply additional derating, between 20 and up to 55, 60%, like we just said. And then it says this is in a raceway, and then there's a different chart for free air, and then a different chart with wind that has different ampacities listed. And then different cable jackets, we've already pointed out they have different temperature ratings, and so a cable jacket with a higher temperature rating can hold more amperage and have less temperature derating due to heat than a cable that's not designed for a harsh environment. And that really comes into play when you start using indoor cable versus outdoor cable. They can make indoor cable a little bit cheaper, and that cheapness means you can't do as much with it. So now we're looking at some just basic conductor ampacities, and we can see that there's a wide range of cables, but a number 8 cable that's rated for 40 amps. If you're using a kind of a cheap indoor cable, there might be another number 8 cable that is rated for 55 amps. So what do all these cable numbers mean? They were engineers, and so we like to label things, and we like things to have a very technical meaning. We're going to, just in a couple of slides, we're going to get to a section in code that explains. Here we go. We talked about this yesterday about even when you're throwing cables into a trench, you have to space them out in order to avoid them being considered to be bundled together for heat dissipation. Going the wrong way. There we go. So now we get to a section that defines what all of those table wiring acronyms mean. MI stands for mineral insulated. These are conductors. Sorry, not cables. We have a plastic skinned cable. We have a moisture resistant plastic skinned cable. And so what we're seeing is this moisture resistant has this W in it. And then this doesn't have a W, and this one says it's moisture resistant and it has a W. That W is a sign of a wet rated cable. Now you could have other wet rated cables that are more kind of industry specific, that these are more just kind of general acronyms that you go to Home Depot and you see either THHN cable, which is just a single conductor, high temperature cable that's not for a wet environment. It's a common single conductor cable that's put into homes. Some of these have specific meanings. MI being mineral insulated, underground feeder, UF, underground service entrance. So we have service entrance conductors. We also have this -2 here. This -2 indicates sunlight resistance outside of conduit rating. And so before there was a solar industry specific cable, we were using a lot of say USC2 cable in solar because it was thick enough that we could find it with a thick cable gauge. A lot of this THHN and THWN is done at smaller cable gauges or utility scale cable gauges. And this has a wet rating, sunlight resistance rating. Cables have different cable jacket thicknesses, which can impact how many fit into a conduit. A lot of the conduit calculators are based around THWN and THWN2 cable. Technically the amount of cables that you can fit in a conduit has to do with the area, not the actual cable. So, you can calculate conduit fill percentages without using an online calculator by finding the areas of the cables based off their exact cable jacket dimension, and that's listed in code. What this extra thickness does is it's like the skin of a water balloon. The thicker a plastic is on a water balloon, the more likely you can drop it on the grass without it bursting apart. But the moment that blade of grass hits that water balloon in the right way, cuts through it, boom, there's a explosion. Voltage is kind of the same way. It's how much pressure, that electricity inside the cable can exert on the cable. It's how much water you can squeeze into that water balloon before it explodes, rather than like heats up or deteriorates or melts. So it follows that wet rated cable is a little bit thicker than dry rated cable. If you have an indoor cable, it might have a thinner cable jacket. You replace it with an outdoor cable, then that outdoor cable might not be able to fit so well into the conduit. And furthermore, it's that thicker cable jacket inside that conduit is going to retain heat in the cable a little bit better. So by and large, you want to use indoor cable inside and you want to use outdoor cable outside. Maybe for for a very short run, sure. Now you do get cross-listed cable, so I'm often using THWN2. That's an inside a conduit cable, and just going from the inverter outside the house through the house and then up to the rooftop. Okay, so we started yesterday talking about damp and wet locations. There's actual requirements on metal versus non-metal on whether or not you can just drill the backside of a box directly into the wall. So a lot of professional listed metal equipment will have drill holes that are offset from the back of the box slightly to create that air gap. But if you just bought a generic metal box and screwed it directly to a concrete asphalt wall, that could be a code violation. The temperature differential between the wall and the hotter inside of the box could cause moisture to accumulate, which you don't want around, electrical terminals. But it says, well, if it's plastic, that's fine. Plastic, better insulation, you don't have that issue. Let's see, there's spacing requirements within the box itself to make sure that your live parts are not close to the lid. If you're looking at your electrical box and it's made of metal, and then you're looking at those terminals that are energized hovering a couple of inches off the box, like, well, if I touch those terminals to that metal, what'll happen? You'll cause a ground fault. So you can't get these, if you're building your own box, you can't get too close to the edge or the lid. So here we have one that's a switch overcurrent device enclosures. Splices, taps, and feed through conductors are permitted when the conductors do not exceed 40% of the cross-sectional area of the box. When the total assembly does not exceed 75% of the area. So what does this mean? Well, sometimes you have to splice into a box. Here's a component called a tap connector, and essentially, this is when you're doing that supply side tap. You're bringing, the power comes in from the power company and then goes out towards the comes in from the power company. And you use a bolt to tighten down that lug, and then there's a metal interconnecting bar inside this thing. So you have the power company conductor, the grid, and then you bring in your solar array or your battery inverter in blue, and then you have your electrical load coming out the other side. So this is a tap connector because it taps these three cables into one. We saw earlier that is if they're within 10 feet of the service, then there doesn't need to be overcurrent protection in that line. Anyway, these knuckles take up space. They're larger than the cabling itself, and so what we see in National Electric Code is rules governing both the how large the box needs to be in order for you to not just pass the conductors through the box, but also to do work on them. And then also, the cross-sectional area of the entire box. And we're going to see these requirements reappear in National Electric Code when it turns out to be like, well, what can you put in a box and what can you not put in a box? With smart homes, you want to put energy monitoring equipment inside an electrical box sometimes, and or a electrical service panel. Hey, can I put this device inside my service panel? There may be some more specific rules, but the general rule is, as long as you're not exceeding 75% of the cross-sectional area of that box, one dimension or another, then you're going to be fine. But then on top of that, you want to make sure that you're keeping live parts, away from the door. So that brings us to, can you do if you're allowed to have splices inside of raceways or inside of boxes or inside of conduit, there's some exceptions to say, well, you might think you can put a splice connector here, but you actually can't. So we're getting into smaller conduit bodies. This is called an LB, and you have conduit coming in one way and conduit coming the other, and you use an LB for two reasons. The first reason is you're doing a cable pull and you need to go off the other direction. Generally speaking, with cable pulls, you can, well, not just generally, literally speaking, you cannot pull more than 4 bends. So if you have a 90-degree bend, a 90-degree bend, 90 degrees, 90, that makes 360. And once your conduit forms that circle, then you can't stick your fish tape through it and pull out the cable from one end to the other. It becomes too hard. So you'd put in an access point to better accomplish that cable pull. Well, the other aspect of when you use LBs is when the customer says, I like the way these LBs look better than a 90-degree bend. You could have a 90-degree bend, but if this were done with a 90-degree bend, it would start bending over here and take up a lot more required space to do a EMT tube with a 90-degree bend, whereas with an LB, you get a nice sharp edge. And my experience has been clients don't like it when you have big loopy cables coming, over the edge of a building, that they would prefer something that hugged the profile of the building with a nice sharp edge. I'm going to talk more about that in a minute. But what this rule is saying is, hey, if you have an LB, a small conduit body, just for really pulling cables through and getting you, an access point for your cable pull, that's too small. LBs that enclose conductors number 6 or smaller shall not contain splices, taps, or devices. So we do have a caveat that says, hey, if this LB gets large enough, if you're doing big utility scale work and you have one cable coming in and another cable coming in, you want to put a tap there, you may be able to do that inside larger conduit bodies. Small conduit bodies should not contain splices or taps. Okay, so there's a difference between a cable and a conduit. And there's a difference between a conductor and a cable. And so here we're seeing, this is a conductor table where all of these are single cable conductors. So, this cable has multiple conductors bundled inside of it. Romex, for those AC circuits all throughout your house, has multiple circuits bundled inside of it. And so code has a section for single conductor cables. They also define multiple conductor cables. And then, the way it works is your multiple conductor cables, you're not pulling through anything. They already are kind of done for you. Whereas otherwise, if you're using single conductors and conduit, you build your conduit run and you pull your single conductors through it. So the question is, well, when do you use a pre-made cable and when do you not use it? And, in general construction, using a pre-made cable, if you can get away with it, it might cost a little bit more in material, but you make it up with labor. Now, the problem with solar cable specifically is DC solar cable inside of a building needs to be in metal. And so Romex does not work with solar for running cables through the inside of the building. And that really led to, installers needing, smaller than utility scale cable for home projects, for residential, small solar projects, but not having any product availability. And so the solution was, well, we'll run our metal conduit and pull single conductor cable through it. There is an option, though, for a bundled cable. It costs 3 times as much as in material as buying the conduit and putting the cable inside of it. But by the time you add in everything up, I find it worthwhile. I never regret having it on a job site when we can use it. The pros of metal clad cable, this is not flexible metal tubing where you buy the metal conduit empty and then you pull the cables through it. This comes with, they actually wrap this binding around the cable, and that actually has a difference. If you put this in a larger tube, so that you have to have the empty space so that you can actually pull this cable through, and these ridges make it, and the flexibility of the cable both make it very difficult to pull cable through this stuff. And so you get a hollow flexible metal conduit for short sections where you're pulling single conductor cables through. But because this is more tightly wound around the cables themselves, you get more flexibility in this. And so what this is you can get it in a 1,000-foot spool if you want. So generally I am measuring the runs between the rooftop through the attic and down to wherever the inverter is, and I'm buying enough metal cable to make that run, and I'm just pulling it through the attic and strapping it up to the top of the attic. Not within an inch of the roof, but up at the top in a nice orderly way, and that avoids having to build a conduit run. So when can you use metal clad cable? Some jurisdictions don't let you use this. And I'd say so if you're in a major city that is, I'd say, on the east or the west coast, multi-unit building, they might have a requirement to say, no, we want you to use conduit that's a little bit stronger than this metal clad cable. But I think for solar, this, having this metal is, hey, none of the other power lines in your house are in metal, and the utility feeder entrance conductors inside your house don't even need to be in metal, and they're at a much higher power capacity. I think that this metal protection is really for critters, so that they don't chew up your power lines, and I think that can make sense. That this is one area where the United States has a more expensive solar industry than in other countries, but you get what you pay for. Landing the connectors on this MC cable, if you over tighten them, they can bite into the cable and cause a ground fault. And also metal clad cable, the attic that it's in has to be accessible. You have to be able to kind of see it and walk around it and be able to get up to it. And finally, the last thing with MC cable is it can only be in a damp environment rather than a wet environment. And so generally with this MC cable, here's the house. And if you're putting your inverter on the north side of the building and the solar array is on the south side of the building, here's your solar array up on the rooftop. What I put a specialized metal box right up here on the rooftop, and then I run MC cable through the box, strap it through the attic, and then out the other side. At this point, you have to end your MC cable right underneath the soffit so that it's still protected by the weather. If you run your MC cable all the way down to the inverter, the inspector might say, well, that's not rated for that. So what you can do is buy the length of MC cable to go down to the inverter and then just peel off the metal wrapping and then transition that into EMT conduit. So when I'm buying my MC cable, one of the things that I'm checking is, hey, even though the MC cable has a damp rating, I want to make sure that the cables inside of it are THWN, are wet rated cables, so that I can put it into EMT conduit at that point for the rest of my run down to the inverter. But that actually, it simplifies the installation, because instead of taking your conduit and like snaking it over the side of the roof and around the roof and then around the roof again and then down to the inverter, you can just drill a hole in the roof, throw your MC cable over the other side, and land on your inverter. It's much faster, and I feel much better knowing that the cables of the solar array are protected by the home structure rather than exposed to the great outdoors. And so how hot does it get on a rooftop? We saw 60-degree temperature adder can actually go into PV watts and look at your rooftop temperature in your area. So you go to PV watts, download the hourly data, and you can explore the coldest temperatures and the hottest temperatures. Maybe not on record, but in your normal operating environment. You can assume the cold temperature side of things is going to be a little bit harsher. And generally, when you're looking at your temperature conditions, you're using the record low, but they let you get away with the ambient high because that hotter temperature, to some extent, is going to start dragging back your system performance. So, anyway, how are these fires starting? Well, code has gone a little disconnect crazy. This is over in Australia. This is not a US code thing. Australian code and US code have a lot of similarities. Believe me, there was a time when US code was looking at doing what they do over in Australia, which is putting a disconnect switch right alongside the array up on the top of the roof. It's like, okay, well, there's roof-mounted air conditioning units and commercial settings have disconnect switches. The problem with a disconnect switch on a rooftop is not the switch itself, it's the roof. It's a very hot environment. And by cutting that wire inside that disconnect, you're inserting a failure point into the system. And the terminals on those boxes where the cable hits the box is one of the hottest points on the system. Now, wherever you get a failure, wherever you get a splice or an inefficiency, and electrons are having to leap over that's not a good, strong point within any electrical system. Down at the cell level, you get impurities on these solar cells. Electricity starts hopping across, and the cells can start to degrade along the line of the little micro crack that the electrons are jumping over. So a terminal point where the cables come in and landed on a metal bar gets hotter than the rest of the box. And so the problem becomes when you build a solar array, then you're like, oh, I need to have a box up on the rooftop. So you go to Home Depot and you buy a box and a terminal bar, and you're not using solar specialty parts, but you're just using stuff that they have at the supply house. And this more generalized balance of system material stuff might only have a 60-degree temperature rating or a 75 C temperature rating, whereas everything else, your solar cable, your solar panels, the inverter, everything else in the system is designed with a 90 C temperature rating. And so if you've been doing all of your temperature calculations, assuming a higher temperature rated device, and you go and swap it out with a lower temperature rated device, then we saw with those temperature correction factors that the temperature derating for lower temperature devices, oh, come on. We saw that when you use a lower temperature device, that the derate factor is substantially larger, 70% instead of 40%. And so the rooftop isolator boxes in particular, especially when you're not using specialty solar high rated temperature devices, you're just going to the store and buying something off the shelf, you might have a temperature mismatch, at which point those terminals become the hottest part in the system and can smolder and catch on fire. Another aspect is debris can accumulate underneath the solar array. And if you get debris accumulating around that box, that can be a fire hazard as well. To the point where it's not a bad idea to budget a little more money and put a metal netting around the perimeter of the array. Most installers don't do that. I'd say it's not a standard practice, although I know solar companies who have it be a standard practice. What I would say is if there's trees nearby, to the point where it's not just that there's branches nearby, but that you could get leaves falling onto the roof under certain conditions. If you get leaves on the roof, you want to have a net around your array so that those leaves do not get underneath the array where they can get caught up on the racking and the wiring. All right, so now we have some more rules for metal clad cable. Secured at intervals every 6 feet. 10 feet for vertical drops within 12 inches of a box. We say, so. I guess you don't need to attach it to every single rafter as you're going across the rooftop. And here's another kind of cable, power cable, TC cable. This stands for tray cable. And what we'll talk about in a minute is something called cable tray and how useful it is, particularly on commercial job sites. Tray cable probably can go inside a cable tray. It's probably cable that's designed to go inside of cable tray. And it says assembly of 2 or more conductors. So that's why we're calling it cable rather than a conductor. It's a cable with 2 or more conductors, with or without a ground. And it has a non-metal jacket. So MC cable is metal clad cable. TC cable is general plastic without the metal cable. You might put it in a metal enclosure. It says TC ER cable is permitted as interior wiring. It's a non-metallic sheathed cable. It's also robust so that it can be direct buried. It gets that outdoor rating as well. So TC cable is a common cable, and it's commonly used for like AC microinverter circuits too, where you won't have to put it in metal at all. So normally if I'm doing microinverters, running TC cable, from the service panel, up to the metal box that's kind of built into the roof, the transition box is fine. Service entrance conductors are also useful in the solar industry. Service entrance could be underground service entrance, and a lot of utilities will not have underground conduit from the side of the road where the power transformer is to your house. Maybe only 10 feet of that will be conduit, and then they'll transition into the earth just to make the pulling and the installation of that underground cable easier. So USE cable is useful for ground mounts, direct burial. Some other kind of wrapping up our cable discussion, some other types of cable. There's intermediate metal conduit, which is a little bit stronger than EMT conduit. Then there's rigid conduit. Rigid is pretty common to be waterproof and watertight, whereas EMT, metal stuff, that's used indoors pretty frequently where you're already in a dry environment. And so you can in the solar industry, we're not trying to have a lot of money spent on our conduit, a lot of protection on our conduit, and we're usually going in with EMT conduit. But you have to check the weather ratings, to make sure that your fittings are rain tight rather than just indoor. Whereas rigid, those fittings for rigid are usually always watertight, also much more expensive. There's flexible metal conduit. It looks like metal clad cable. We were talking about it earlier. Then we have this liquid tight flexible metal conduit, and that's pretty useful because it's metal, and so DC wiring, solar cable has to be in metal when inside a building. B, it's flexible, and so sometimes the end runs of your conduit having that flexibility is useful, or being able to run it through an attic can be useful. And it's liquid tight, so it's waterproof. So this is a conduit that can kind of do everything. Running liquid tight flexible metal conduit from the roof down to the battery room would be a code compliant job where you don't have to worry about anything. In battery rooms with lead acid batteries, you have to paint or insulate the cable to prevent corrosive deterioration, and this plastic on the outside of it is worthwhile. Now, where this liquid tight flexible metal conduit gets confusing is that there's also a flex conduit that doesn't have any metal in it, and that's just called flex conduit. So the liquid tight flex metal flex is how you would refer to this ordering it at a supply house. We got PVC. This is not white plumber's PVC. It's gray. It has a little bit better deterioration ratings. So let's see. Flexible metal tubing is not permitted in battery rooms. That's that metal tubing with the holes in it, because battery rooms can have corrosive gas. They want a more solid enclosure. So we can use liquid tight flexible metal conduit instead. Costs more. And finally, so now we're getting to something that isn't conduit, called gutters. And a lot of kind of self-educated electricians, solar installers, this is where they start to not have as much experience. The gutters still have that 40% fill, 25%, 25% conductor fill, and 40% or 40% conductor fill and 75% cross-sectional area fill. I think this is staying away from the edge. What do these look like? All right, some pictures. So we're making our way through the wiring and cabling section of code, and we've defined conductors, we've confined cables, we've defined conduit that would surround conductors, and now we're getting to even more rare kind of enclosure called gutters. I'd say rare. You can walk around and see them, but they're these long rectangular prisms that it's common just to see EMT little stubs of conduit going down into. So here we have little conduit stubs going down into this gutter. A couple of conduit stubs going out into this gutter. And what does that gain you? Why do we use these gutters? Well, because otherwise you would have to take this run, and let's just assume this is from a solar array and it's landing on this inverter, or maybe it's probably going back to the electric service panels. The solar stuff, I'd say, is going to come in through here. But if you didn't have these gutters, you would be running conduit down and looping it around on the wall in these big loops. And then you might have multiple conduit runs. So over here on the left, we have 4 EMT runs up to this section of the rooftop, and we have 4 EMT sections running off onto that section of the rooftop. And each one of these sections has to be bent and made up and attached and drilled and knocked out, and then the fish cable put through for your conduit pull, and then that taped off and tied to all the conductors that have to be prepped individually when you're pulling them, so you can pull them through all at once. And on this particular project, the plan set called for EMT conduit, and it turns out this is material wise, it's cheaper than that, which is cable tray. You really only see cable tray on commercial systems because of its cost. It's, even by the foot, you're getting into I'd say $12 or more. And so that can get quite pricey for the conduit run. But what does it gain you? Why do we use it in commercial jobs? And even here in this, I'd say high-end looking residential project, this is not my project, it's Ben McFeeder's on Facebook. But he's using, gutters as kind of like a residential poor man's cable tray. And this, it depends on, that DC wiring needing to be in metal. This is probably the DC side. If you wanted to be completely code compliant, maybe inside here you maintain some metal, or you make this particular box metal and have this be AC and have it be plastic, or these might be metal gutters. I can't really tell if they're plastic or metal from here. Well, if you use gutters or cable trays, then you're just making this run relatively simple. There's parts in cable trays for flexibility, and then you can just kind of walk through and lay in and line the cable into it. So the actual cable run itself is substantially is faster. Now, on top of that, getting all of this straight, making all the bends perfect, and all the kickoffs and setbacks is difficult. When we initially installed this, what the array ends up here. So we said, okay, we got a 90-degree bend, and then another 90-degree bend, and a third 90-degree bend, and then our fourth 90-degree bend to land on here. So we could have use 2 sticks of conduit and have a nice smooth bend. I personally don't like using unnecessary LBs. This is, instead of, we're not making 4 turns before we land on this LB, and we're not making 4 additional turns before we land on that LB. What happened is the client came back out and said, well, we see your conduits looping off the side of the building and looping back down, and we're like, well, yeah, that's what's on the plans. And he said, well, okay, well, we did define it. We want our vision was that this conduit hugs tight the building. So, we redid it to make it look better, and admittedly, it does look better, but also admittedly, cable tray should have been specified instead. Because by the time you end up, you evaluate all of that work, you're spending as much on labor instead of getting a higher quality finish. So what the gutters do is it allows you to simplify all of this stuff. We have 8 different circuits or 8 different conduits that might contain 2 or 3 circuits in them landing inside here. And each of these circuits needs to get divided between multiple inverters, and then also come out and go into a broader box before we get back, to our main point of interconnection. And so what the gutters do is allows you to grossly simplify all your cabling coming in and out of the various conduit runs. And it also gives you these nice and straight little short stubs between one section to the next, so that you don't have to deal with all the complicated bins and parts and fittings. But this sort of stuff is best pre-designed. See, we have I just wanted to include this slide because it's a mention of electric vehicle cable, which is a high voltage cable of conductors of various sizes. That's kind of interesting. It's a little bit more of a flexible cable. I'm used to using kind of welder's cable for inside of large battery banks for ease of wiring. Might have to look at the EV cable instead. There's a solar cable too. It's called PV cable. It's high voltage, super thick jacket, exposure for sunlight, high temperature, wet environment. All right, so now we're making it into section 400, which is general equipment. So this again has a lot of repetition because it will cover, batteries, for example, even though batteries have their own section later on. So, maybe when equipment in the general equipment gets to be so special that they warrant their own section of code, code gets expanded and shoved off towards the end. But we got switches, like a big old knife switch disconnect on the side of the building. Can you use switches as a raceway? It says enclosures should not be used as a junction box or a gutter or a raceway for conductors feeding through or tapping off to other switches unless the enclosure complies with a certain section. We already covered this section. That's the section where it's talking about the 40% full with conductors or 75% full with other stuff. So you are allowed to, put a tap connection inside a box, inside a meter can, inside a device, but not if it fills up more than 75% of the surface area. So damp or wet locations. So we have to make sure that if it's in an outdoor environment, if it's wet, if it's underneath an awning, that we're using wet rated boxes. Since we have this picture and we're not too far away from it, it's a little hard to see, but there's these little black connectors on that EMT, and you can kind of see these little black connectors here. And then on this picture, this indoor picture, you don't see, they're just metal connectors. You don't see any coloration. That's the difference between an outdoor rated connector and an indoor rated connector. The outdoor rated connectors have a little bit more stuff on them. Actually, Um, Yeah, so basically these rain tight EMT connectors have more robust caps and inserts on them to prevent rain from getting into there. And the thing about it is these rain tight EMT connectors, you have to buy them at your supply house, and they're rare because it's really only solar installers who use them, as far as I can tell. Most other outdoor electrical products are either going really low end and are AC and are not, shrouded in metal like an air conditioning circuit, or they're high end commercial industrial projects and they're using rigid instead of EMT, and rigid's already rain tight. And so the availability of these rain tight EMT connectors, you can't find them at your box stores, and often they're a special order item at your supply house. So that I think is a common kind of error. And maybe if you're putting outside of conduit cable inside of that EMT, you might argue to your inspector that we're just doing this conduit for physical protection, but we're not required to be in conduit, so the environmental rating of the conduit doesn't matter. I don't know of I'd say inspectors would go 50-50 on that argument. If you're using inside a rated conduit, like THWN2, it's a wet rated conduit, but it's a cable, but it's not rated to go outside a conduit. You would still need to respect the environmental ratings of the conduit. I mean, just because you're using rain tight fittings on EMT conduit, it doesn't mean the inside of that conduit is in a dry environment. So here's an interesting one. It says for switchboards and panel boards and switchgear, the directory should not be handwritten. And so, we'll see in labeling requirements, locating disconnects, putting inverter voltages and amperages. Back in the day, we would just have stickers that were blank, and we just use a Sharpie and write the voltages and amperages on the label. It's more professional, if not required. There's certainly parts of code that say, hey, this placard or label cannot be handwritten. And so if you're field labeling something in the field today and writing in numbers with your hand, it's tomorrow's code. They might say, oh, we haven't updated that section, but they could easily roll out none of this stuff is handwritten anymore. It's not too hard to get custom printed stickers made, and so we want you to do that instead. So unused openings shall be closed. So what that means is if you drill into a box for your conduit run and then you end up not using that hole, there are plugs you can buy to fill that hole. You don't just leave a hole inside your electrical box, because you'll get wasps and critters nesting inside, which is a nuisance by itself, but could cause issues too. Panel boards, switchboards, and switchgear should be 3 feet from the ceiling. Overcurrent protection of panel boards. So what does that mean? Well, we have a service panel, and it has its breaker slots on it, and then we have our main breaker. That's our overcurrent protection for our panel board. It says the panel board shall be protected by overcurrent protection having a rating that's no greater than that of the panel board. Okay, well that makes sense. If it's a 200 amp, service panel, we can't, as its main breaker, have that be 240 amps. Otherwise, it's not, going to be compliant. Sometimes you'll get a 225 amp main breaker on a 200 amp panel, but if you go and look at the inside of it, they've actually given that bus bar rating a 225 amp rating. It's an unusual circumstance. And so they say, okay, there might be some different circumstances. We'll talk about that in the interconnection discussion in a little bit. Just in the interest of time, I'm going to kind of move the discussion along so we can get into batteries and solar. This is saying for backfed devices, there's a additional requirement where the backfed device needs to have not just be snap-on, but be a screwed in. But then they give you exceptions that cover solar panels. So we'll get to those exceptions later. Panel boards need to be connected to grounding. We'll see this come up again. So grounded conductor terminals. Let's just keep going. So we have sections for motor controls and motor circuits whose overcurrent protection sizings might be a little bit different than normal. So with a motor, you have a throttled controlled output, and you don't want the motor to be running too hard and overheat and load up. So I believe with the motor overcurrent protection, it's not a 25% oversize, it's a 15% oversize. These terminals are still hot at the very top. And electrician, is comfortable looking at these terminals and the energized from the top, but still nonetheless opening up the lid to that disconnect switch and maybe even working on the underside of the switch away from this energized area because they know what they're doing. Someone else could misinterpret this switch being down as off and this lid being open to reach in and touch those terminals because they want to do some amateur wiring work and electrocute themselves. And that's why these readily accessible disconnect switches need to be locked so that only people who should be in them can get in them. Another lesson on these disconnect switches is you have a top group of terminals and a bottom group of terminals. And so the question is, which side does the utility land on, the top of the terminal or the bottom of the terminal? You might have an underground feed from the utility, and your wires are coming up into the box from underground, and the solar array up on the rooftop. You might just say, okay, we're going to put the solar array on top and the utility conductors on the bottom, and that's going to look nice and neat. The reason why that's wrong is because it needs to be consistent and standardized that when the box is open and in the off position, that the bottom of the box is de-energized and the top of the box is energized, because by nature of this lid here and height, gravity, the bottom of the box is a lot easier to work in than the top of the box. And so you don't want to encourage work on the dead side on the top of the box by leaning over the energized terminals on the bottom of the box. You want it to be the other way around. And for those reasons, the box is labeled with a line side, which indicates this is the hot side, and a load side, which indicates that this is the bottom side. And in this case, even though you have the grid, which is obviously a supply, You might also have the solar array, which might not have any load circuits on it. So you say, okay, well, which goes into the top? They're both supply. The grid's a supply, the solar array's a supply. Which one lands on the top of the disconnect switch? The answer is the supply that's always on. The grid side goes into the top. The primary side goes in the top. So this disconnect needs to be readily accessible. It needs to have a sticker that warns about the electric shock. It needs to be suitable for use. Abide by the 6-handle rule. And then it says we're going to have you simultaneously disconnect those inverter output circuits. And it's marked line and load. So that's your solar disconnect. If your combiner boxes are large, they need to have disconnects on them. They can be remote operated, similar to the battery disconnect. They need to be externally operable without exposing the operator to parts while indicating open, closed, or lockable. Some jurisdictions take this too far and they say we need to be able to view the disconnect without being exposed to operator parts. And so you need a disconnect switch with a little window in it so that you can look inside the disconnect switch and see it. That's not part of code. That knife switch disconnect where up is down and up is on and down is closed, that you can just pull up to the side of the house and look at that knife switch to see if it's open or closed. That's an indicating closed, lockable, operatable switch. It's not the only, a knife switch is not the only switch that is allowed by code to be this disconnecting means. It's just a very common one. When I'm buying a disconnect switch, it might be cheapest if you're just doing a simultaneous disconnect of each 120 volt pole. It's probably cheapest just to buy a 2-pole non-fused disconnect switch. I've usually regretted buying a 2-pole switch instead of a 3-pole switch to also disconnect the neutral, because you don't have to disconnect the neutral. You can just run it straight through. But then down the road, being able to disconnect the neutral is nice for truly off-grid systems where you don't want to backfeed. The utility's concerned about you backfeeding during a power outage. Being able to disconnect fully from the grid by disconnecting the neutral as well can be useful. But it says it can be a load break fused pull-out switch, like an air conditioner disconnect can be compliant as the solar disconnect. Most local jurisdictions step in and say, no, we want you to use a knife switch. So for identification, solar circuits need to have their own raceways. They can't be combined with other loads. They need to be kept to themselves, but that can include the AC and DC conductors. When sharing a box, there doesn't even need to be a barrier. They just have to be grouped separately. So you can't have the AC conductors tie wrapped with the DC conductors. They need to be identified at all points, including splices. Which one's positive, which one's negative. Identification can be the colored cable plus numbers. Or it could be colored tape plus numbers. Now it says, if as far as single conductor cable goes, we're going to allow you to use USC2 cable, even though it's not specifically listed as solar. It says underground surface entrance cable is robust enough to use as solar cable. And you can also use solar wire, PV cable, or it's really PV wire. It's a single conductor. Shall be permitted as well. Um, what it says in exposed outdoor locations and within the solar array. So, code is saying, look, this PV wire has a very thick jacket. We want you to transition into a thinner jacketed cable when you go inside the house and make it back to the inverter. Or they keep it outside. Cable tray is allowed. Multi-conductor cable assemblies are allowed. Flexible cords for tracking arrays has to be that hard service cord, not EV cord. So here we have the requirement for metal inside the building. So still pretty early in the solar section. DC circuits, when they run inside the building, they have to be contained in metal. From the point of penetration of the surface of the building to the first readily accessible disconnecting means. All the letters on the labeling system have to be capitalized. They need to be every 10 feet. This means every 10 feet on that solar circuit, on that conduit, on that metal conduit, you need to have a sticker that says, this is a solar circuit. So installers have tons and tons of conduit stickers that say, caution, photovoltaic output circuit, or solar source circuit, just to slap on the conduit every 10 feet. Inside the attic, up on the rooftop, all the way back to the inverter. Access to boxes. So junction pull boxes, they can be located behind the solar panels. So what that means is here you're up on the rooftop, and here's your solar array, and here's your solar array, and here's your solar array, and you have a nice symmetric, that's a professional looking roof right there. And the question is, when you make this transition with your box, do you have to put the box outside the array and then run conduit to it and then drill into the roof and go into the roof from there? The answer is no. You are allowed to obstruct this box by putting it underneath the solar array. And it's a matter of professionalism on whether you do this or not, because a low profile box that fits underneath the solar array is a specialty item. So only solar installers really know about like the Soladeck box. Sometimes I'll get a Soladeck box that's just an empty shell and run all the way back to the inverter. If I'm using MC cable, I'll use that Soladeck box to do transitioning from MC to the PV wire up on the rooftop. But I love hiding them underneath the solar array because then you can't see it. Then it results in a magical aesthetic where when you look up on a standard blue rooftop here, if you don't have any stuff outside of the array, you just have your solar array, up on the rooftop, and everything, all the conduit and cabling and racking is hidden, underneath the array in a little box. You achieve this kind of hovering effect where it just looks like the solar array is magically floating on top of the rooftop. And generally what I'll do is I'll take my box and put it at the corner of an array, so if someone's up on the rooftop they can look underneath and see where it is. Likewise, I'll get into the attic and I'll generally locate this box at the top of the array to minimize the amount of rainwater that's going to pour around that penetration. And then that's where sheltering the box with a solar panel is really the nice thing, is because you're getting that box out of the sun, you're getting it out of the rain, you're using the material on site, as opposed to having the box be outside the array perimeter with a little nub of exposed conduit. So it says the equipment ground conductor is run with your solar circuit conductors. When they're leaving the vicinity of the solar array, it should be compliant. It says when it's smaller than number 6, it needs to be protected from physical damage. So this is where we talked about how installers will just run a number 6 bare ground up to the rooftop and land it on the racking and call it a day. If it's smaller than number 6, then it needs to be physically protected. That's where I usually use a number 8 that's wrapped into the MC cable. Identification of power sources. This is the listing requirements. You say, well, what stickers do I need on my solar array? Your stickers need to identify what the array actually is to an inspector or emergency responder when they show up, so they know what's going on. So the difference between if the system is off-grid or grid interactive needs to be called out. The system rapid shutdown needs to be called out. The disconnect locations, array voltages and amperages. Some additional requirements. It says the PV system output conductors shall be marked to indicate polarity when connected to energy storage systems. So positive and negative. So now we're moving into Chapter 7. Chapter 7 governs emergency systems and standby systems. And what's interesting about the two is that they're different. So an emergency system would be, a hospital double redundant or triple redundant, a fire alarm system that might have its own tapped on connection to the grid ahead of a main breaker so that it doesn't lose power when the whole building does. Whereas a standby system is backup power that doesn't have these like life critical operations. So I would caution you in discussion with clients to refrain from calling battery backup systems as good for emergencies. Use that word sparingly, because in code it has a very different meaning than what we would think of as emergency power. And standby systems are still regulated as well. And a battery inverter might not be a standby system if the battery system is not large enough or capable of providing backup power. It's just there to manage grid electric bill issues. It might not even be a standby system. Although most solar customers kind of expect that. But here's the thing: even with standby systems, it says, look, if you're going to have a load on an automatic transfer switch so that you don't lose power during a non-emergency power outage, it's a typical power outage, your source has to be capable of supplying the fully connected load. And this is the real reason why when you look at a standard battery inverter, like the SolarEdge battery inverter, it's a 7.6 kilowatt battery inverter. But then they have a critical load side of it that's only like 5 kilowatts or maybe 2 kilowatts. It depends. But or like with the Tesla Powerwall, the power goes out, the Tesla Powerwall doesn't back up your entire house through its output. It has a critical load side that gets transferred and runs critical loads off the critical load side. And why is that? And it's because whatever loads are connected to the critical load side, code says you have to be able to power them. You can't have a critical load panel and turn it on during an emergency and it not work because it's overloaded. And so having your whole house on a backup system would require delivering enough power to supply your whole house. And that would mean you'd need a much larger and much more expensive system. And that's really frustrating to customers because they say, well, can't during the emergency I just use a little bit of power and not as much as I would normally use. The what code is saying is automatic transfer equipment needs to be capable of supplying the fully connected load. So that does leave a little bit of gray area for interpretation in terms of, well, what if you actively manage your devices to put them into an emergency mode setting? But a rigid inspector could say, no, if your battery solar system is not rated to supply, a 200 amp service, we want you to use a critical load panel. And that is frustrating too, because you might want to back up during an emergency way more devices than what you would normally use the system to power during normal grid operation. So you might not want to manage all of your devices under a normal operation, but if you did manage them under an emergency setting, that could create a different operating condition. So we're starting to see, and we talk about this in the smart home load control class, that energy management has never been easier. It's pretty easy now to get the air conditioners and the freezers and dryers and water heaters to operate at different times. And that's opening up the new possibilities for standby power that code is not, it'll have to be updated. So the supply side connection of the system, it says all of the overcurrent devices connected to the power sources should not exceed the rating of the service. What does that mean? So I have a main service panel with a 200 amp breaker. And on the grid side of it, it's connected to that utility transformer on the side of the power pole. And these conductors are being run down for a 200 amp service, and these conductors are rated for a 200 amp service. And so if I take a solar array and I connect it into these conductors, 120 volts per leg, what's the largest solar array I can plug into these conductors? Well, the answer is the rating of the service. This is a 200 amp electric service, so we know when the utility put in these conductors, they rated them for 200 amps. And so we know that the solar array largest output that we can tap onto these conductors is 200 amps. And another reason why we can do that is all of the electricity into the service panel is being regulated by this 200 amp main breaker. So whether or not the electricity comes from the grid itself or comes from the solar array, by the time it hits the actual service panel, it's regulated by this overcurrent protection. The minute it goes above 200 amps, that breaker is going to trip. And there's no possible way that this service panel can pull in more than 200 amps. Oh, that would be different if we have our 200 amp service panel and we're pulling 200 amps in from the grid, and then we go and we connect the solar array not to the power lines going into the house, but to the electric service panel itself. Because let's say this solar array is 40 amps and the grid is 200 amps. What that means is we could feed the panel with more than 200 amps. On a commercial project, you might have a 200 amp solar array divided between multiple inverters, and this is a 200 amp panel, and you count up the solar inverter breakers. Let's just say these are 50 amps each, and you'd say 50, 100, 150, 200. This is a 200 amp panel. Okay, I'm good to go. That's pretty easy. On a residential electric service panel, you have a 200 amp service coming in from the grid, and you go and you count all of the individual breakers on that service panel and add them all up. You're going to get more than 200 amps because code assumes not all of these breakers are going to be on at the same time. And so if you have 300 amps of breakers and you put solar on the supply side, it doesn't matter because you can only pull in 200 amps because of the size of that main breaker. If, however, you go and you put solar on the load side, you could pull more than 200 amps through this 200 amp service panel because the breakers are so many. And so in a way, the connecting to the supply side, connecting between the main service panel, and the electric grid, maybe the meter is right here and you're connecting on, the customer side of the meter, but the utility side of the main breaker. This is a supply side connection, and you can go all the way up to the rating of the service. The other kind of connection is a load side connection, where you go into, as we were saying earlier, the bottom of the bus bar here. And so for load side connections, it says, all right, you take 125% of the output circuit of your design amperage, plus the rating of the main overcurrent protection device protecting the bus bar, and that shall not exceed 100% of the ampacity of the bus bar. So what that means is if I have my main breaker, which is 200 amps, and then I have my solar breaker, and let's just call that 40 amps. And the thing is, even though it's 125% of the power output circuit, here's your solar inverter, and here's your output circuit, and you're sizing it to be 125% of this output. So it's like the ampacity of the cable, but then you're just rounding up to the nearest breaker. So there's only like an amp or 2 or 3 difference between using the breaker size or using this 125% size. So just to make things simple, we got a 200 amp breaker and we got a 40 amp breaker. And that gives us 240 amps of power. And so if this is a 200 amp service panel, it's going to heat up and burn if we supply it with more power than what it's rated for, except in one circumstance. And that circumstance is when the supply of the power source A and the supply of power source B are located as far away from each other as possible so that their mutual power sources kind of get used up before they interact with each other. So the bottom source feeds the bottom loads, and the top source feeds the top loads, and they don't mix to combine to be more than 240 amps or whatever. if you just plug in this solar inverter wherever you want it to go, then the feed from the grid and the feed from the solar could combine together and overload the bus bar. But National Electric Code says, okay, we're going to give you a little bit of wiggle room if you interconnect at opposite ends of the bus bar. So what this means is, this is called the 120% rule. And what it means is, if you have a 200 amp service panel, you can have 200 amps coming in from the grid and 40 amps coming in from the solar array, provided that they are on opposite ends of that service panel. So it's very common on solar arrays that are 40 amps or down, just to land them on the bottom of the electric service panel. Although not in all circumstances. In some cases, supply side connections are easier. In other cases, load side connections are easier. I personally think that you have to think about your disconnect switch locations, and at which point one can be better than the other. If you're doing a supply side connection, you're putting in a larger system, because that lower amount doesn't work. And so if you have your electric service panel here, and you're intercepting these conductors between the grid and the solar array, you might want at this point to put in a 3-pole disconnect switch so that you can fully isolate the home. You might want to put that switch right here, so that you can fully isolate the home from the grid. So if you're doing a supply side connection, I think you need to start thinking about automatic transfer switches for the whole house, and start building the infrastructure for whole house backup. Maybe not doing everything today, but at least putting in the appropriate disconnects and switch gears when you're already working in that area. And sometimes it's easier just to keep it simple, and for systems that are 40 amps or down, kind of just land onto the service panel until you're ready to do something more ambitious. The problem is, by the time you get the solar array and the battery bank next to each other, you start to run out of space on the service panel anyway. Inevitably, if the home is going to be powered with whole house off grid, whole house battery backup, inevitably there's going to be some type of supply side interruption and interconnection. And so we see field labeling. It says, if your connection, if you're doing a load side connection using the 120% rule, you need a sticker that says, hey, don't relocate this breaker. If you're not using the 120% rule, then it doesn't matter where the breakers go, and you don't need the sticker. But if you're using the 120% rule, you need to have clear instruction to say, hey, electrician, don't move this breaker, because it has to be located down here. Likewise, if you're working on a load side connection, you need stickers that say, hey, be careful about adding more breakers to this service panel, particularly loads, because you don't want it to exceed the ampacity of the bus bar. Center fed panels are allowed to use the 120% rule just on one end, but not both ends. So that used to be ambiguous. That's been clarified in 2020. So equipment containing overcurrent protection devices must indicate the presence of all power sources. So an electric service panel has to say, hey, this is a solar circuit right here, regardless. We see the disconnect requirements are the same as the solar disconnect requirement. They have to plainly indicate whether it's open or shut. That doesn't have to be a knife switch, but you have to be able to look at the switch and see if it's open or shut. Lockable, simultaneous. It says the location of the overcurrent protection device has to be within 10 feet of the electrical service. What that is does this, if you have power in the meter going into the property and your solar array is really far away from it, the required disconnect is within 10 feet of the electrical service. Now, you might have to have an additional disconnect if it's typically within 50 feet or line of sight. If it's outside of line of sight, then you'll have to have another disconnect here. It's a matter of principle. But it says location of overcurrent for that device. That overcurrent could be a breaker. It could also be a fused disconnect switch. Sometimes you can save yourself a bunch of money if it's just one solar array being tapped into the grid, to not put a service panel there, but instead just you're already buying a disconnect switch. Using a fused disconnect switch counts as your overcurrent protection. Chapter 7, we got some special conditions. Interconnected power current. This is kind of like the DC optimizers. You're using the inverter output current, and then adding 25% to that, unless there are other active controls already going in line. I guess what that means is, like, if you have a output current and it's rated for 40 kilowatts, and you put a fuse in there that is or let's just say it's a 800 amp output system, and normally you size it to be 25% more than that, but if for whatever reason the manufacturer says put in a 900 amp fuse in line, then you could size it for 900 amps. That's a rare circumstance. This is saying you don't need to have that extra fuse. You could get away with a non-fuse disconnect if there aren't any parallel power circuits. If it's just the solar array going straight into the service panel and that's it, as long as the short circuit current is there, it's fine. Let's see. If the inverters, we just talked about this. If the inverters are not in readily accessible locations, then they need to have disconnect switches within sight of the inverter. Basically, there needs to be a disconnect switch that a worker can look at and use, when they're working on the equipment. There also needs to be a disconnect switch where emergency responders that are just pulling up to the house right at the electrical service can press to de-energize the system. And if these locations are not both adjacent to the solar array, then you need to have disconnects in both locations. Ampacity of the neutral conductor. There's special considerations for 240 volt inverters on three-phase wiring versus 120 240 with regarding oversizing. And so on three-phase 240 volt, you may not be able to undersize the neutral. I think that's what it is. Just know there's a special exception there. Or there's another exception that says if the neutral isn't needed by the inverter to function, then you can just size it to be the equipment ground conductor size. We kind of talked about that in the early part of class. Hey, but now we're making it almost all the way through code, so just a few minutes left, and we'll get there. Now, this is our last section, Article 706, Energy Storage Systems. Now, we already saw a section in 480, General Equipment for Batteries. This is saying battery systems that are operating at over 60 volts DC that may be standalone or interactive with other power production courses. So you could say, okay, well, operating at 50 volts AC, that's going to be most battery inverters are outputting over 50 volts AC. So we're batteries for buildings is being pulled into this scope. You can say, well, what about 60 volts DC? My battery's under 48 volts. Maybe. I don't think it matters. I think you got to abide by energy storage systems because I think you want to be looking at battery systems that are over 60 volts. And I say this as someone who hasn't done it before. I've only done 48 volt battery banks, but I've only done lead acid battery banks. And we saw that lead acid has a lower native voltage than lithium ion, which means that at low voltages, all else being equal, I can fit more ampacity for the same number of batteries with lead acid than I can with lithium ion. But what I know about lead acid on a 48 volt nominal battery bank, by the time you're getting up to 122 kilowatt hours, which is about what you need to start really providing whole house off grid to most solar homeowners, is that you're getting up into a volt times an amp is a watt. And so if I'm designing a system to have, let's compare 12 kilowatts and let's compare 48 kilowatts. Let's pull up our calculator and do some amperage calculations. And so let's say I'm designing a battery system for a whole home, and that whole house is a 200 amp service panel. You have to remember that that's 200 amps at 240 volts, and a volt times an amp is a watt. And so your home service panel is 48 kilowatts. If I was trying to draw 48 kilowatts of power, and that's my service panel power, but it's going through my battery inverter. And if my battery inverter is drawing off a 48 volt battery bank, that, if we're going from 48 volts to 240 volts, the voltage is increasing 6 times. Volt times an amp is a watt. And so the amperage is increasing rather substantially too. Instead of a 200 amp service, or 4 times, instead of a 200 amp service, we have 1,000 amps coming out of that battery. That's parallel runs of incredibly thick battery cable. Now, you can find lead acid battery that's rated for 1,000 amps output, but your battery cable sizes are getting into the size that you'd use for utility scale facilities. With incredibly high amperage, you're spending too much on your cable. What's more typical is a home to have maybe 12 kilowatts as a backup solar inverter, but even then you're using 250, 300 amp cable and getting up into 4-aught, which is like the thickest welder cable you've seen. And you're beyond 4-aught, that gets you into utility scale, cable. And so what is safer and what is more cost effective is to increase voltage and decrease amperage. And so with the Tesla battery and with other kind of battery inverters that were made specifically for lithium ion, you see in electric vehicles, for that matter, you see moving towards like a 350 volt platform. And that, taking what would be a 48 volt battery and making it into a 350 volt battery is, that 7 or 8 times increase is going to drop your amperage 7 or 8 times as well. And that means you'll get away with thinner cables in your system, which are easier to manage, less costly. Higher voltage is cheaper than higher amperage. So we're going to be moving away from the 48 volt kind of home backup power standard and into higher voltage battery banks. And this is the section that governs that. So we have different system classifications: self-contained, pre-engineered of matched components. That's not you doing the design. That's a manufacturer selling you a battery product that is really the combination of a bundle of products that are still designed to work together rather than just being made by one company. And then other, which is like, if you hired me to build you a battery bank, this is what you'd get. Someone would piece together systems, buying different batteries and different inverters from different supply chains. And that's a standard construction project. And so we got some labeling requirements, such as the clearing time of that electricity coming out of the battery conductors. So when you disconnect the battery conductors and you measure their voltage, how long does it take for them to drain to ground? We say when a storage system is more than 5 feet from its connected equipment, or if they pass through a wall or a partition, you need to have a disconnecting means at the end of the circuit. And I recommend getting knife switch disconnects in this case so that no inspector says, and you need to disconnect the positive and negative at the same time. A second disconnecting means needs to be located at the equipment if the first disconnecting means is not within sight. So we need a fused supply side disconnect at the battery terminal when the two locations are more than 5 feet away from each other. So if you only want to get away with having one disconnect in line of that battery circuit, those batteries need to be within 5 feet of their end run. So that's pretty strict. The batteries have to be right next to the inverters to have simplified disconnects. So here's the one we talked about earlier, where there needs to be a minimum of 1 inch clearance between the battery and the wall. Well, then you go and see nice pictures of like the Tesla Powerwall being mounted in a garage. It says, the trays can actually touch the wall in under 2 circumstances. You could build the shelf into the wall, but then you'd need more than 1 inch of space between the batteries and the wall. Or you can use like a Tesla Powerwall that comes pre-engineered to hang on a wall and is listed for that. And they say that's okay too. And we see requirements for egress and illumination that we've seen before. Conductor ampacity should be not less than the greater of the nameplate circuit current rating or of the energy storage overcurrent protection device. So the conductors, your battery conductors, have to be sized to be at least the size of the fuse that's protecting that battery circuit. And that should be not less than 125% of the battery circuit, kind of a standard thing. The location of the overcurrent, if you're more than 5 feet away, should be at the battery itself rather than at the equipment, so that it fails at the battery rather than at the equipment. All right, so dwelling units, not permitted over 100 volts unless the live parts are not accessible during routine maintenance. So if you get into high voltage battery banks, even within that locked storage room, you may need a partition if there's other routinely maintained equipment inside that room. This is kind of interesting. It says if you're building your own battery banks, then you need to isolate the batteries so that it break them down into 240 volt or less segments for maintenance. It says floating batteries are allowed. Okay. Yeah, that's where you have a disconnect switch on both ends and fuse both ends. It's pretty common. It says flexible cable is allowed within the battery. So sometimes flexible cable is finely stranded cable, and it's frowned upon in electrical usage because of arcing, and it's less of an ability to hold up to when it's being landed on a terminal and the bolts screwing into the fine strands. They chip off. It says, well, in a battery enclosure, you really need that extra flexibility. Flexible cables are fine in a battery enclosure, still sized to 125% of the current. There are some other sections, off-grid standalone systems or direct current systems. Chapter 8 is where you get into communication system cable.